First thing I want to talk about is derived units. And again, when we talk about derived units, we have quite a few derived units in science, and some of you may already use derived units, you just don't realize it. In other words, if Terre Haute is about 65 miles from here, and it takes me 1 hour to get there, what is my rate of speed? 65 miles per hour. That's a derived unit. Okay, so in other words, we're taking two units and we're putting them together. Back when we did we use, I'm trying to remember the constant, Planck's constant when we were working with light?
Yep.
The joule seconds, that's also a derived unit. So you don't have to divide the units, they can be multiplied as well. All right, density. Hopefully everybody remembers what density is talking about, but again, it's defined as the mass per unit of volume. So it's a ratio of the mass to volume, which is nothing new there. Calculating density, again, the equation that we'll use is density is equal to the mass over the volume. And a student showed me this about 8 or 9 years ago. I kind of like this. It's called the density triangle. And it integrates the equation density is equal to mass over volume. So if you want to go and do an equation, here's how we do it. And whenever you move this way, you're multiplying. Whenever you move this way, you're dividing. So if I want to know what the equation to solve for density is, it's mass divided by volume. If I want to find out what the equation is for mass, I do density times volume. If I want to find what volume is, then I do mass divided by density. Now again, we always show our units, but the units will also verify that we have the calculations set up correctly. So the types of calculations that we're going to work with today, sometimes I'll ask you to calculate the density, sometimes I'll give you the density and the volume and ask you to find the mass, and other times I may give you the density and mass and ask you to find the volume. In other words, you'll always know 2 of the 3 variables to solve for the unknown. Okay. And that's it for that. Okay, so let's take a look at, there's 2 practice problems. There's 2 practice problems that I want to go over here, and then the rest is your homework. So there's 2 practice, and then there's 6. Yeah, six really good ones. All right. So number 1, it says calculate the volume of a piece of a certain metal that has a density of 4.33 grams per centimeter cubed and a mass of 75.2 grams. Now, don't forget that when we do these, the units for this. Actually, let's do it larger here. Okay. So again, it's grams per unit of volume. Now, I think in the lab we didn't use centimeters cubed. What did we use? What did we use for our volume?
I don't know, that was like 3 weeks ago.
It was a while ago. What was it? Milliliters, good. So if you have milliliters, that's a volume unit. How come we don't cube that? It's already a volume, very good. And it's nice to know that if you have 1 milliliter, that's equal to 1 centimeter cubed. That's a nice conversion to have in the back of your mind. You may also hear on TV or over here a doctor say, hey, give them 20 cc's. What's a cc? Cubic centimeter. Okay, so we don't ever use cc's in here, but that's also the same thing. We don't use cc's, and I don't know if they do it in Project Lead the Way or not. Okay, so a cc is a cubic centimeter. All right, so all of these are equal to each other. So there's your volume. So we could go grams per milliliters or grams per centimeters cubed. I've also seen it as kilograms per liter. All right, so it can be a lot of different things. Also, the mass, some form of mass, and again, so again, we're going to let our units help us make sure that everything's working out here, or it could be centimeters cubed. Okay. All right, so let's look at the first problem. So we always want to know what we have, and it says calculate the volume. So we're actually looking for the volume. Okay. So does anybody remember the equation for volume for that? Mass over density?
0.36.
Oh.
That's
So again, we're going to verify, or at least I'll do it here, that we're actually getting a unit for volume, because we just don't want to throw numbers in there and hope it's right. So what's the unit for mass again? Grams. And what's the unit for density? Grams per milliliter. Okay. Or centimeter cube, which I think is, in this case, whoop. So let's go centimeters cube. Okay. Now, what is our final unit there?
Centimeters cubed.
Centimeters cubed. Again, if you talk about the inverse of the inverse, in other words, if I do the inverse of 1 over x, what does that equal? X. All right. I think we may have talked about that earlier. So really the grams cancel out, and that's another reason why I'm not a big fan of having two division signs. The way that I would really write this would be this, and I'll put centimeters on the opposite side of the grams. Okay, so the grams cancel out, you're left with your unit that you're looking for. Okay, so that's just a nice little refresher from what we talked about earlier in the year. So we do have this equation here where it's volume is equal to mass over density. The mass in this problem is what?
75.3.
There you go. And the density in this case? 4.33 grams, and I'll put the centimeters cubed here again. Grams cancel out. What unit do we have? Centimeters cubed. And then make sure your calculator. Yeah.
Where's your cool calculator?
They're all cool.
No, the other cool one.
So 17.4 centimeters cubed. Okay. Let's look at the second one. Ooh, look at that. Percent error. What's the equation for percent error? You guys did it on your lab.
6%. The true value minus the lab value.
Good, okay. So true value minus lab value.
Equal.
Or if you did lab minus true, tomato, because again, we have our absolute value. Now, some of you had negative percent error. You didn't listen to that. So make sure that you actually drop the negative. And what are we dividing it by? True. Very good.
True. So
And then, of course, multiply it by 100 to get your percent. Okay. So that'll always be provided for you. And I would write this at the top of your paper since I don't see it on here. So right up here somewhere for you. Okay. So number 2 says, calculate the percent error for a measurement taken in the lab for the melting point of a certain pure substance. If the temperature was taken at 155.3 and the literature value, which is the true value, is 169.8. Okay. So I'm going to erase that. So our percent error, we have, what is it again? Temperature was taken at 155 minus 169, and it's divided by 169 times 100. So anybody get an answer? Good. Okay. Now if you left a negative in your calculation, drop it, because it's dropped here. Alright, so the other problems are doing some percent error and using this equation here. Okay.
easy.
I like it. Giddy up. We're cooking. Uncertainty in measurements, and the 2s are part of your homework as well. So far, I think you have about 4 minutes of homework. Whenever a measurement is made by a device, this would be a graduated cylinder. one of these things, and we'll get to use some of these here shortly. We have to guesstimate on some readings, okay? But we always write down what we know, for sure. And then we don't want to do something like, here's what I would not do. I would not look at this and go, that's got to be, well, let me ask you what you think it is first. If you were reading this, do we read it, and this is what's called the meniscus, okay? Do you read from the bottom of the meniscus or the top of the meniscus when doing that? The bottom, good guess, it's 50-50, good odds. Okay, so we know that we have at least how much in here? What are we certain of? Yeah, we know we have at least 30 milliliters. Is it safe to say we have at least 35? Okay. So it's safe to say that we have at least 35. Can we say for certain that we have 36 or 37? No. So since we don't know what this value right here is, okay, that's our one uncertainty. We know for sure that we have 30 milliliters in there. We know we have at least 35, but really we're guessing when we say that we have 36 or even 37. Okay. Here's what you would never do. You would never look at this graduated cylinder, especially with those types of markings, and go, yes, that's 36.75873.2 milliliters. Duh. No, there's no way. I mean, we're guessing on this value right here. So when we go and write more decimal places on here, you're just throwing garbage around. There's no way you could prove that those actually exist. So we write down what we know for sure, and then we write one uncertain number. So I know there's at least 30. I know there's at least 35, but I'm really guessing if there's 36 or 37. And guess what? I would accept 36 or 37 on that. I might even go out on a limb and accept 38, but you'd have to really impress me on that one. Okay, so whenever we read instruments that are not really well marked, don't go crazy and try to tell me what the values are there. Okay, that's what all that was talking about. And that gets into significant figures, which you guys are going to absolutely love. You guys ever worked with significant figures before? Ugh. Oof. Everybody had the blink so far? Alright, significant figures or Sig Figs. Significant figures is a way, it's a means by showing that the numbers that you're writing down actually are important, or they have relevance. Okay, just like with that example with the 36 point whatever I wrote down. The point whatever has no relevance. It's just, that's what my calculator gave me, all right, or something like that. No, don't write down too much stuff. And just because your calculator spits out a value that goes all the way across the screen, don't write every number down. Okay, so we're going to talk about significant figures. We've already talked about certain digits in a measurement plus one uncertain one. That's cool. Okay, we'll use that only in the lab. But we also want to be able to look at a value and ask yourself, hey, how many significant figures do we have? Any number, if I gave you a number, okay, or it's on your homework or something, if it's a number that's other than 0, it is significant. So like for example, the number 96, there's both of those numbers are non-zero numbers. So both of those are significant. 61.4, all those numbers are significant. However, that 0 in front of the 0.52, I'd be willing to bet that probably half of you would only, whoops, that's my habit, sorry. I'd be willing to bet that half of you probably would only write that. And you know what? That's fine. This is just eye candy. Okay? It really is. It has no significance. It's just there because I like it. Okay? Some of you like it, some of you don't. That's why you don't show it. Okay? So that 0 is not significant. Okay? when you anything that is following a decimal point, okay, and there are trailing zeros, they're always significant. So in other words, what you want to do is look for the decimal and then ask yourself, okay, is there a non-zero number before my first zero? And this is where it really gets fun and confusing. Since these are all non-zero numbers, you have 3 sig figs. Since I have a non-zero number here and here, these zeros are significant. This is probably where you're going to come back and look at the video. Since I have a decimal place here and I have a non-zero number to the left of a zero for the decimal, those are now significant. Also with that one as well. And you're like, what? It gets better. We'll do some examples here in a second. Captive zeros are always significant. However, zeros that do not have a decimal before the non-zero number or even a decimal are not considered significant. This is crazy. Since there's no decimal there, only the 7 is significant. These zeros are simply placeholders. Since there are no non-zero numbers before this 7, there's only 3 sig figs. These are only placeholders. Okay? You're like, what? So just remember, if there's a decimal, now they're all significant. No decimal, then only the non-zeros are significant. Aren't you glad you got out of bed this morning? This is what drives my students nuts. Even AP students go crazy on this stuff. Exact numbers. Okay? When we talk about an exact number, we're talking typically about conversions. So like if I say, oh, how many centimeters are in 1 inch? How many centimeters are in 1 inch? Does anybody know? I'll always give it to you, but I'm just curious if anybody knows. I heard 2. Yeah, you got one of the numbers right. 2.54, yeah. So there's 2.54 centimeters in an inch. And don't stress out, I would give you that conversion. Those are considered exact numbers, and we would never use those values to determine significance. Oh, there it is right there. Sorry. All right, now for the fun part. Multiplying and dividing with sig figs. Oh, Lordy. Anytime you multiply and divide with significant figures, you're going to run your whole calculation through on your calculator. And then you're going to look back at your values and ask yourself, okay, which of these has the least number of sig figs? Whichever of the numbers that you're given. I'll do an example here in a second. And that value will tell you how many significant figures are in your answer. Let me see if I have one. I don't. But let me use this open space. Let's say that I have 7,324, and I'm going to multiply that by 20.1. Okay. So if you have your calculator, type that in. See what you get. So 73.24. That'll give you a chance to use your calculator. In my calculator, spit this number out. 147 point. Oh no, that's a comma. God, I hate that function on there. 212.4. Okay. So that's what my calculator spit out. When you multiply or divide, and I'm not doing a division here, but it's the same principle. This is what my calculator spit out. What would I write on my paper? Well, you want to look at these two values. Ooh, what happened? How many sig figs are in this top bag? 4. Very good. How many sig figs are in this bottom bag? 3. We have a captive 0. So what you need to do is look at it and say, okay, well, there's 4 sig figs there. There's 3 sig figs there. So my answer will have how many significant figures? 3. Yeah. So you look at the two numbers, whichever of these two values, or however many values you're multiplying, you want to look for the one that has the least number. So on your paper, you would write either that, because there's only 3 sig figs in your answer. What's another way I could write that? and still only have 3 sig figs. Learned about it earlier today. Very good. And what would that be? 5? Okay. So either or. If you start having numbers with a bunch of zeros, you're like, I've written about 4 zeros here. Get in the habit of writing scientific notation. Okay. So again, when you multiply or divide and you're looking for significance, look for the value that has the least number. Again, this one has only 4 sig figs, this one has 3, so my answer will have 3 sig figs. Okay. Make sense? It's not too bad. I think multiplying and dividing is actually easier. All right, so let's look at adding and subtracting, since I said that. All right, when you add and subtract, and you're concerned about significant figures, you do the math, you add them all up, or subtract them, or do whatever when you're adding or subtracting, and you want to look for the number with the least number of decimal places. So it's all about decimal places when you add and subtract. So for example, and that's how many decimal places your final answer will have. So if I have like 23.47728, and I have, and that's added to 17, well, my calculator is going to spit out 40.47728. That's what my calculator is going to spit out, if I did that right. What am I going to write down as my answer? 40. Okay. You can either write 40 or 40 with a point. Either one of those would have been correct, because they had the same number of decimal places. When you add and subtract, you look for the value that has the least number of decimal places. Since that one doesn't have any decimal places, there shouldn't be any decimal places in your answer there. Okay. All right, so let's look at some of the practice problems here. Practice problems ask how many sig figs, or how many significant digits are in each of the following quantities. In A, how many sig figs? 1. Okay, remember that if there were 2, there would have to be a decimal to capture that 0. How many sig figs in B? 3. Very good. How many, without doing the math, how many decimal places should be in our answer? 2. Very good. So recognize that we're adding and subtracting, or adding and subtracting. So our answer, whatever the answer would be, would have 2 decimal places. How many decimal places would we have, or do we have in D? Sig figs. Sorry, sig figs. 5? Did I hear 5? Yeah. Good. How many in E?
9.
All of them. Good. Is that 9? Yeah. In F? 3. Excellent. How many in G? All of them. Good. So 11. Everybody get that? Isn't that good? So you'll have some of those in your homework. All right, the last thing, and this will be really quick, so we'll be done here shortly. Precision and accuracy. We often, and you'll use it much better now after today, we use precision and accuracy so interchangeably in our everyday conversations, if you use precision and accuracy, that it's brutal. And I'm going to tell you why precision and accuracy are actually different. Okay, so there's a little story that I have on there. Let me find an open space. Here's a good one. Let's say that I have 2 targets. I don't know why we'll do that. Okay. Okay. So I've got 2 targets, and I've got a BB gun, or a gun, or whatever it is. I don't know why I'm looking at this, but I've got a gun, and I'm looking at the left target, and I'm an excellent shot. I can't hit the broadside of a barn with a gun. So I fire off 3 shots. Pow, pow, pow. And they hit right here, right here, right here. Okay? I give the gun to somebody else. They line it up. They're focusing on this center spot right there. That's what they're aiming at. And they fire off 3 shots. And much better. They're hitting boom, boom, boom. Okay? Then I give it to a couple other people. And those same results keep coming back. What in the world's going on? Is the gun broken? No. But what? Sight's off. Okay? In other words, if I'm aiming here and I keep hitting here, the sight is off how? Up and to the right or down and to the left? Actually, up and to the right. So if I'm, like if there's a rabbit coming across, if I'm lining it up in my sight, and again, you can get used to doing this, and I'm not saying I hunt or anything, but if I'm tracking something and before I pull the trigger, I'm going to drop my gun, boom, fire. Does that sound like a really good way to do it? In other words, track it, knowing that your sight, if I'm aiming right here, I'll hit it here. So just follow it, and then before I pull the trigger, pull it up, I'll nail it. That's stupid. However, we have things in our house and in this lab that are very, very precise. In other words, when you get on your bathroom scale, if there's still bathroom scales around, we don't have one. When you get on it, I get on there and I'm like, woo, yay, whatever the weight is. I want to lose 10 pounds. You know how I can do that? Step right off, bend over, dial it back 10, woo, lost 10 pounds. Okay? So that everybody that comes on, woo, I lost 10 pounds. Everybody's getting the same results. That's precise. Okay? If I aim at the bullseye and I hit the bullseye, that's accurate. Okay? So we know where the center is, we know where the bullseye is, and we hit it. That's accurate. If we know where the bullseye is, but we're okay, knowing that we're only 10 pounds off, but everybody's 10 pounds off, this is also acceptable. Now, if you have equipment where you shoot here, 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 okay, then you need to look at the operator. Okay, so that's the difference between precision and accuracy. And I think, unfortunately, this is one of the longer lectures, so I hope I didn't bore you to death. But I think there weren't any. Oh, and percent error, I will give you this. We'll work this one out together